Hello, good evening, and a warm welcome to the Bay Area Apache Spark Meetup group on the 12th eve of this beautiful meetup here in San Francisco. I'm really heartened to see so many of you here today. My name is Jules Damji, and I'm the developer advocate and community advocate at Databricks, and also the program chair. So I'm really happy that all of you are actually here today. Now, it's actually people like you who actually make these meetups and make this community grow at this astonishing rate. It's actually a momentous occasion for us. As of this morning, I checked, we have about 575 meetup groups globally, and with over 500,000 members. That's 575 meetups globally and 500,000 members. That's amazing. And it's actually because of people like you that only last week, this particular meetup actually reached its 10K number of members. And it's because of people like you that this community or this Spark has actually created a global movement that actually has no borders. So give yourself actually a big hand of applause for being here today, for crossing the lands and crossing the oceans. So thank you a lot for coming. Now, there are a couple of things that I will make some announcement before we actually have our first speaker on board. Those of you who actually came in late, we had some slides rotating. There's a lot of things happening in the next 3 days. There are going to be 3 birds of feather sessions happening, 2 tomorrow and 1 on June the 6th. We got Apache Spark and Kubernetes tomorrow, and there's going to be the machine learning productionizing during the lunchtime. So if you go during the lunchtime, you'll see a table. There'll be a signage that says BOFs. So if you want to ruffle some feathers and you got a chip on your shoulder, you want to express that, please come and ruffle some feathers with some contributors and communities, members in the Spark community, so you can actually have a good camaraderie there. And then the following day, on the 6th, there's another BOF called Apache Arrow and Pandas UDF, which is a new feature that was added in Apache Spark 3 that allows Python programmers to do UDFs at scale. The guy who wrote that is going to be there, so it'll be good to actually have some of you participate while you're having a bite. There's going to be Women in Lunch data on June the 6th. Come and join the women to find out what, how impact they're actually making in big data. And then finally, there's going to be a final meetup on Thursday from San Francisco and friends at the Mesosphere on June the 6th at 6 p.m. Now, before I actually introduce my first speaker, I just wanted to acknowledge Databricks for giving us this particular space and the organizing committee to actually having it. Now, my first speaker, you guys have probably heard about machine learning algorithms, and you probably wondered how Apache Spark parallelizes them, you know, or on a single machine with lots of cores, or on multiple machines and multiple cores. How does it actually do that? And to tell us all about it is my esteemed colleague, Richard Garris. Now, Richard is a principal architect at Databricks. He helps clients to do machine learning deployment at scale. And he's here to tell us all about it. So please give a big warm welcome to Richard Garris from Databricks.
Good evening, everyone. You guys hear me? Awesome. Welcome to Spark Summit plus AI 2018. How many in the audience use Spark today in their work? How many people? Okay, everyone. All right. How many people do machine learning with Spark? Okay. How many people use other frameworks? How many people use Tensorflow? Tensorflow. H2O? H2O. Scikit-learn? Okay, we're going to talk about all of those frameworks today in this talk. A little bit about myself. So I'm actually part of the field team. So I work with customers on their machine learning as well as their big data use cases. So we have a team of 10 people right now. We're also hiring. So we're looking for people that are as passionate about data, as passionate about customer obsession as we are. And we're looking for the next people to help our customers kind of grow. So just quick shout out if you guys are looking for a new position. So a couple things about my background. I've been doing this for the past 3 years at Databricks, doing it 15 years overall. And I have degrees from Carnegie Mellon and Ohio State. Go Bucks. So here's a quick agenda. So we're going to talk a little about machine learning overall, just to give a level setting of machine learning as an overall view. Talk about machine learning as an optimization problem. We're going to talk about logistic regression, talk about single machine versus distributed algorithms, as well as techniques for parallelization, as well as a quick demo and Q&A. So many of you have seen this, so everyone knows AI is changing the world. Whether it's self-driving cars, I used to work at Google, and you have Waymo, you have Alexa and Google for doing things like speech recognition, AlphaGo, beating the best players in AlphaGo, using these algorithms. It's all there. But it all starts with really machine learning plus AI. But the key to all of these algorithms is really the data. So Andrew Ng calls the algorithms the rocket ship, and the data the fuel that drives the AI. So what is machine learning? So for this talk, I'm really going to talk about supervised machine learning. So obviously there's unsupervised as well. But I'm really going to talk about how you can actually teach a computer, kind of like my t-shirt here, teach a computer how to learn from a set of examples, how to predict something in the future. So there's really two parts to the machine learning. One is the featureization. That's the ability to turn all the data into something that can be consumed by the algorithm, as well as the actual machine learning itself, which we also call the estimators. What we're trying to do is take all these examples of past behavior and use it to train an algorithm to actually produce what's called the model. The model is what's going to be used to actually predict things given a new set of data you haven't seen before. In its most fundamental concept, a model is a mathematical function. If you guys remember high school algebra, fx, right? So you're trying to learn this function. There's a couple different ways you can do different functions, whether you're doing artificial intelligence like convolutional neural networks, doing linear regression, or doing decision trees. It's all the same principle. You have a set of inputs, you have some kind of function, you apply those inputs, and you have an output, right? So in this example here, linear regression is one of the more, I don't want to say simplest, but most common machine learning algorithms. Here I'm trying to learn a linear line based on my set of data. Another common function is a decision tree. Here is where I'm learning a series of splits. So taking decision trees like an if then else function in programming. If you're trying to learn this based on your actual data set and where to split this data. So as an example, let's say I'm trying to decide if a car has high mileage or low mileage. You might first split on like one attribute like weight. So if it's heavy, then it is high mileage. If it's not, but it's still high horsepower, then it is also high mileage. This is a quick example. Okay, so I'm going to use an example throughout this presentation for bank marketing. So how many people here have heard of Signet Bank? I want to see if there's one person. Anyone know who Signet Bank is? Okay, how many people have heard of Capital One? How many people know that Signet Bank was actually the company that started with Capital One? It was a small unknown bank that learned that based on its prior data could actually better market to the right customers to give them credit cards. So they did this back in the 1980s before data science was really a thing. And then since then they've grown to one of the largest credit card brands in the world, largely based on using data. So an example, this isn't Capital One's data. This is a bank in Portugal. But the idea is here you have a set of information about a person, whether it's their age, the job they have, their marital status, whether they have a loan with the bank or not. What we're trying to decide here is whether this person can actually open a new deposit account with this bank. So the theory here is that if I can actually better target the right customers with the right offer at the right time, they'll convert over to actually opening a deposit account with the bank, so I don't have to reach out to the whole population and waste a lot of money with ads or mailers or what have you. But the problem is that given this set of data, with all these set of examples, how can I learn a function that's going to predict the left column, which is opening a new account, given the data set, by using a function like logistic regression as an example? So machine learning is an optimization problem. So for those that have done computer science, that's really the key to computer science. It's minimizing the amount of work the computer has to do to actually learn something. In this case, how do I, as quickly as possible, come up with the most optimal equation, given my training data X, that solves for Y? Depending on the algorithm, you're trying to learn different things. In GLM, or generalized linear regression, you're trying to learn the coefficients, i.e. the weights, based on the examples, and fit a line of best fit across the points, or fit a sigmoid curve if you're looking at logistic regression. In decision tree learning, we're trying to learn the splits, where you split on the various features based on the information gain. And the idea is you want to minimize the amount of work done so that when you get the result, it yields the best possible result, which means the lowest error, without having to run for an infinite amount of time. Okay? Getting to the optimal model is called convergence. Okay. So error. So there's two different ways to think about the optimization problem in machine learning. One is you're trying to maximize a value, otherwise just think about minimize a value. So you're talking about a metric like AUC, which is a positive metric, the higher the AUC, the higher the accuracy, the better the model is, then you're looking at a maximization problem. You're looking at errors to minimize the error, so you want to actually get to the bottom of the function. So the goal is to actually use a subjective function or loss function to measure the result of the model each iteration, and eventually get to the point where the model is the best possible model you could find given the data set. So as you see here on the right, I do this in Databricks, and you can also do this in IPython or Jupyter. I'm looking at each iteration how the model changes. So the first initial model started at an AUC score of approximately 0.88, and then slowly it kind of fluctuated between 0.88 and 0.87, and then eventually got up to roughly 0.9, given my iterations. These are how all of the machine learning algorithms work in MLlib. It'll actually iterate over the data set and guess which are the best coefficients for the data set, and then once it gets the right one, it'll actually say this is the best possible model given the data set. So one of the things you have to do as part of the machine learning is you have to split the data into train, tune, and test samples. The reason for this is that you want to train on a set of data, but you want to have another set of data to actually test, to actually validate that the model is actually generalizing, learning from the data set. The other set that you use typically if you're doing tuning or validation, meaning you want to try a different set of hyperparameters, is called the validation set or tuning set. All right. So the amount of work. So one of the things in Spark MLlib, as well as other machine learning algorithms, is really important to create algorithms that scale linearly, which means that if the amount of data doubles, the amount of time it takes for the algorithm to run doesn't triple or quadruple or go do a quadratic. This is very important because you don't want to have a situation where your model just runs forever, your training runs forever. So there's a couple of different examples. So just going back to computer science, if you're looking at ON, that's a worst case scenario. That means that for every single row, you're going to actually take that amount of time to run something. So just a case in point, if I'm doing a simple search of 1,000,000 values, say it takes 1/1000th of a second to run this search comparison, looking at a 16-minute runtime, which is pretty slow. You at least want to get to the binary search, which is O log n, which means that this would actually take only 6 milliseconds to run. Even better, some kind of a hash. A hash search doesn't require any sort, doesn't require any computation. You can do that in under a millisecond. Let's look a little at data representation. So for those who have done a lot with Python as well as pandas, the whole idea is that with the pandas, it's all on a single machine, and it's represented as a data frame. But it's represented as Python data structure, so it's not distributed. RDDs are Spark's foundational data structure, resilient distributed data sets. It's represented as a reference to partitioned data. So it doesn't have to necessarily fit on a single machine. It could be distributed out using HDFS or S3. The idea is that it would be something where you can do an analysis of data more than the memory of a single machine. Data frames sit on top of RDDs. They're the strongly typed, optimized, distributed collection of rows that are made up of RDDs. One thing to note is that all machine learning algorithms, all of them require data to be represented as vectors, an array of double values, in order to train the machine learning algorithm. So you can't feed a machine learning algorithm a color like red, green, or blue. You have to give it some kind of numeric value in order for it to learn from it, because fundamentally all machine learning algorithms are based on math. But machine learning is more than just thinking about a simple algorithm like logistic regression, decision trees, even convolutional networks. It's really about a pipeline. You start with your raw data set, you have to extract your features, train your model, and then evaluate the model to see if it's accurate. But real pipelines require a lot of work. This is where Spark's success has really been able to hang its hat on. It's been able to take all these different data sources, do joins with those, extract features, do custom ETL to transform the data into data you can use for machine learning, do multiple feature transformations before you get to the actual machine learning training. So I'm going to talk a little about how you can actually parallelize this. So Spark has always been known as a distributed compute engine to parallelize all this work. But for machine learning, often you may not need to parallelize the actual machine learning training. You may need to actually do the parallelization for the ETL, but then you want to do single machine for the actual training side of it. So you may want to feature engineer in Spark so you can actually gather your source data together, perform your joins, do complex ETL and feature engineering. It works really well when you have big data for your transactions, but smaller aggregated data or subsamples once you're ready to join on them. You need to keep in mind that you may need to have a larger driver size node that can fit all your training data into memory. You may also need to adjust this parameter, Spark driver max result size, in order to collect all the data to the driver. By default in Spark is 1 gigabyte. Often you may need to increase that. Then once you've already done your parallelization, I'll show a demo of what this would look like. Then you can use scikit-learn, open source R, Tensorflow, potentially with a GPU, or other single machine learning to actually do your training. So just to illustrate that, you may do all of your featurization up to this point, and then do single machine when you're ready to train your model. So parallelization technique number 2 is training the entire model with distributed machine learning. So this is where MLlib shines. So really, if you're using MLlib, it's really meant to do millions and millions of instances. The idea would be that you want to create a single model based on all of this data. So in this case, you can see here on the right corner, you're actually using distributed compute to actually learn the gradients based on the data set. And so you're actually distributing out that computation. And that only works when you have lots and lots of data. So you'll create a single model. You may want to do train, tune, and validation split across these models. And for doing, I would say, general purpose machine learning, doing things like decision trees, ensemble tree methods, any generalized linear regression, MLlib is a great fit. If you need to do distributed deep learning, then Horvath, which Alex is going to talk about in a minute, you can use for distributed TensorFlow. XGBoost is another algorithm or another framework to do distributed GBT, as well as H2O also supports distributed machine learning. So technique number 3, and I see this actually very commonly, is actually to train a model on every single worker. And the reason you do this is that if the data set you want to actually train on is relatively small let's say per customer, per set of hyperparameters, per set of features, you may not want to do that across all your nodes. So for that case, it'd actually be useful to actually do a model for every single worker versus doing a big model based on all your data. There's a project called Spark sklearn, which allows you to adapt scikit-learn to use Spark to do distributed hyperparameter tuning, which I'll show you a demonstration of in a minute. As well as in Apache Spark 2.3, you can also use cross-validation and parallelism across the hyperparameter tuning to actually do model selection, hyperparameter tuning in parallel as well. You may also need to broadcast your data to actually train the model on all your data, but actually do a slightly different model on each of the workers, which is very useful when you do hyperparameter tuning. So in single machine learning, such as scikit-learn, all the data is represented as a single band of memory, typically as NumPy vectors. In a single machine case, most of the time the algorithm iterates and loops over the data in a single thread. Sometimes some of the algorithms support multi-core, most of them don't, but it gives you the option to do that. And the way this works is that as error is calculated, the error from the previous iteration is less than the tolerance, and then the algorithm stops. Otherwise, it'll continue to go until it reaches the max iterations. In distributed machine learning, the data is represented as an RDD, which is typically in distributed file storage, such as S3, Azure Blob Storage, or HDFS. As a best practice, you can cache your data in memory across a node so that each iteration won't actually read from disk, which is very expensive. And then the actual algorithm, which is largely based on map reduce, actually calculates the gradients just by distributing the computation across all the different nodes. After each iteration, which is happens from the driver, it'll continue on to the next iteration and try to find the next best model given what it learned from the previous model, and it'll either stop when it hits max iterations or, again, the tolerance is reached. So I'm going to talk a little bit about these algorithms. Obviously, a deeper dive would be appropriate in either Coursera or a college-level course, but just to give you an idea. So we're going to talk about, in this case, a binomial or a classification problem, so I'm talking about logistic regression. So the idea of logistic regression is I'm trying to fit a sigmoid curve over my data set. Given my previous example of bank marketing, here's the probability of opening an account, and here's the actual one feature. This is the duration between the last previous call. So I can see here that based on this fit of the sigmoid curve, that there's a higher probability of a person opening an account if they had a more recent call. The further away from the last call, the less likely they are to actually open an account. The idea is that you're going to try to fit this logistic curve using this equation, which is the exponent of b0 plus b1 and the other coefficients divided by 1 plus that same value. In logistic regression, there's really many different ways to do the solver, which the solver refers to really the algorithm. It's how you can actually minimize the amount of work. So this is why I talked about like the big O notation. This stochastic gradient descent, which is very common, LBFGS, various Newtonian methods. I won't go into any details on how these different work, but the idea is that rather than just having random guesses of the best best coefficients, it actually learns based on the previous iteration what is the next best guess given the data set. The other algorithm we'll talk about a little bit is random forest. So decision trees, single decision trees aren't quite as common because they tend to be biased and overfit to your data set. So random forest allows you to have a set of decision trees that are all weighted that vote on the label. This reduces the ability for the algorithm to actually generalize to a new data set. It's a very good general purpose algorithm. It's also able to find nonlinearities in the data set. That's one of the problems with any linear method. So I won't go into too much detail. I'm going to jump into a demonstration in a minute. But if you want to know more about distributed random forest, there's a paper by Google called Planet, which provides a lot of background around how MapReduce is used for distributed machine learning. The idea is that you would actually calculate out the splits given the data set and the split on information gain. And once you reach either the max det, min information gain, or there's no more split candidates left, then the algorithm will stop. Okay. All right, is that big enough? Do I make it? I think I need to make it bigger. All right. Is it big enough? All right. So I'm going to go through this example, then we'll have Q&A. So again, this is based on the bank data set that I showed you previously. So you're here loading the data set from the UCI machine learning repository. Importing it as a CSV file, doing a couple things to parse it out, load it in. So here are the key features. You have the age of the person, their job title, their marital status, etc. And based on all this data about the person, you're trying to learn if they're a good candidate to open a deposit account. So here's the actual data set itself. You see the age of the people, the various other features around this person, and then the why, which is yes or no, whether the person opened an account or not. So I'm going to actually do, just in this case, technique number 1, which is doing parallel featurization, but then doing single machine training using scikit-learn. So I'm going to load the data as a data frame. So this is the data frame input data. You can see it here. It's a Apache Spark data frame. I'm going to do a couple of things here to turn all the categoricals into numeric values. Again, to do machine learning, you need to actually have all these as in this case, doubles, as well as all the numeric columns. I've taken out duration mainly because duration is kind of cheating because you don't know if you've called them until you've done it before, so I took it out as part of this overall competition. I've also taken care of creating a 0-1 for my label. It's done here. And then once I've done my featurization, now I have my training set and my test set. I split it up between these two different ones, doing an 80-20 rule, splitting on a seed. You should always hard code your seed so you get consistent results. And this is where I want to explain a little bit more. So what we want to do here is actually use pandas to actually do the actual machine learning using scikit-learn. So given that I have these data frame, these two different data frames, training data set and test data, again, this is a distributed compute, it's located across all the different nodes. I can actually do 2 pandas within a Apache Spark data frame. That brings all the data into memory of the single machine. So I go back quickly to look at my slide number 20. What's happening here is I have all these different workers with all this different data. They're collecting it all back to the driver. So you have to make sure your driver is big enough to actually handle all that data. So that I've done that, here's the X and Y, or the labels plus the features. And then trained logistic regression is very easy. I give it a couple of parameters, say, fit the model, and this is my actual model itself. I do a quick test score on this, and I get roughly 89% accuracy, which is pretty decent. That's one example. Any questions on that example? Yes, I'll post it on Databricks C on Community Edition. Yep. Any questions? Okay. So technique number 2 is really doing parallel featurization and distributed training. So this is where AMOLib really shines. So I'm going to use a different algorithm for this. I'm going to use random forest with a number of different trees, 30 trees, 40 trees, and 50 trees. And then I'm actually going to train this using distributed compute on Spark. So you can see here that when I did this training, it only did one Spark job, which is really just collect the data to the driver. But here it's actually doing a series of Spark jobs to actually run this model. Now it's not a ton of data, which is why it took like 1 minute and 60 seconds to run, or 1 minute and 0.6 seconds, sorry. So here we're trying to fit the model here, and it's actually doing it using distributed compute. So you can see here this is running and it's actually distributing it out across the Spark cluster. Let's see how we did though in terms of overall performance. So we did the best model, got the predictions, evaluated the model. So it's not quite as good, 0.79. So maybe it overfitted, maybe there's some other issues with it. But again, this is how you would do it with distributed compute, which is largely using Spark to actually distribute out the calculations. All right. So technique number 3 is doing mini models. So basically doing one model per worker. So why this is useful, because maybe you want to actually group a set of models based on a certain feature. Maybe it's a customer ID, maybe it's a user ID, maybe you're trying to tune over some set of hyperparameters for model selection or tuning, or maybe you're trying to do feature selection. So in this case, I'm going to use another algorithm, XGBoost, framework, excuse me. So what I'm going to show you how to do is actually use XGBoost on a single machine. XGBoost also has distributed as well, to actually train this model across multiple XGBoost models. So I'm going to say I'm going to partition based on the education of the individual. I'm going to repartition on education, and then I'm actually going to train the model using this function. So I'm doing here that each of the different workers, I'm going to collect the data as an array. I'm going to call fit on the XGB classifier, and I'm actually going to return the model back to the driver. So you can see here, this is how that works. You actually train the data here, and then you take the first object, and you see here, this is the actual XGBoost model. So it's very popular if you're trying to do something where you have each user has their own model, which would be something you might see with, like, say, Netflix or eHarmony, where each person gets their own specific model. This would be how you would do that using distributed compute from Spark. You can also pickle it as well. And lastly, you can also facilitate this through Spark sklearn, which is a library which allows you to use scikit-learn to distribute out the computation. So in this case, I'm going to try a number of different number of trees as well as a number of different depths. But rather than actually doing that with distributing it in Spark, I'm going to distribute it using scikit-learn. But then I'm going to train these parameters on each different worker. So you can see here this took a little bit less time than the actual distributed Spark job. It took 30 seconds. And I got to the following best estimator given my data set. Any questions? A mapping between the worker and the models? You don't have to. So Spark takes care of that. So if you're doing this, where you're doing a repartition on education, what it's going to do is going to randomly hash and actually set up which worker is going to be assigned to which education that you group by. Oh, yes, I will.
Feature set extraction is the most computationally taxing part of this, and then model training is a distant second. Is that true or not?
It depends. It depends. So often enough, like getting all the data, most data scientists will say this, 60% of the work is getting all the data needed to actually do the training, as well as featurizing it, cleaning it up, making sure it's the right data. So I'd agree with that part of it. But some of the more complicated workloads, such as like doing NLP, doing image processing, requires a lot more compute, which is where GPU and deep learning have really been applied.
A large number of models can run on a single machine.
A lot of it can be run on a single, especially now with like big nodes like X1s and others, as well as the big VMs from
Thank
Azure.
You.
Can you repeat that? I can maybe give them the mic.
Sorry, as a customer right now, I applied a card, right? Based on your model, you predicted it, where I opted for it. Where my data objects doesn't have in your model tuning, but I don't want that advertisement again. So how do you remove from that model?
Remove the test set, or I don't understand your question.
Yeah, so like you have your test set, right?
Huh?
You splitted it. Based on that, you predicted some model where you targeted the customer, right? So as I'm a customer, so where I opted for that credit card. So I don't want that ad again. Right?
Oh, I see.
So how do you remove from that model?
Oh, that's a good question. So you can either prune or you can update the data before you do it. I guess Thunder, you want to answer that? Oh, you're with the background. Okay. No. So you can either do one of two things. And this is where, like, I do feel like logistic regression as well as decision trees actually do a little bit better job of model interpretability. So people manually change the model. So you can actually see all of the if, then, else splits across all the different trees in the forest. You can manually take things out if required, or you can manually prune after you've done some kind of predict function to actually take someone out of that list. Did that answer your question? I mean, so once you have a model, it's just an if, then, else. It's just a decision tree. So you can actually manually tweak it if you need to. So you can manually say that if this parameter is this, then take it out of the entire decision tree. Yeah, you would have to do it for the entire model. You do it manually after you actually can see the model, the actual result. Whoa.
And I have this doubt, like, every year, always we are calculating on a human mind, right? We are predicting that this customer will do like this because of my model, right? But a year, as a human mind, your priorities will change. So now, how do, like, this predicting the algorithm, how that comes into a picture? Like, today might be, this year I like the color of white. Next year I change the color of pattern of red. So now any car, if I need to buy, how do I predict those models?
It's not magic. It's based on a priori evidence. So it's going to use historical data to make the prediction. So if things just change, like the algorithm doesn't know that. If you're a human being, you wouldn't know that either, unless you actually see it yourself with your own eyes. Just like that, a computer is the same way. It's not going to learn something that it doesn't know. Did that answer your question?
Yeah.
Okay.
Thanks.
Yeah.
Okay, come over here.
Thank you so much for your speech. My question is, first, how you do like feature selection when you train the model with 2 algorithms or more, and there is some like conflict, and how you, for example, the first elastic net feature selection result is different from, for example, XGBoost, then how you usually get that done, like manually do the selection. And the second question is, in general, how you tuning the parameters of each, for example, algorithms, XGBoost or random forest.
Yeah, this is more art than science, and some of the parameter tuning that you're mentioning. I couldn't tell you the exact details of why, based on ElasticNet, you have a different set of features that it predicted as being important, whereas another algorithm said, these are the features that are important. It really depends on the algorithm. It depends on like the parameters, how long it ran for, the number of iterations, how much pattern it can find in the data set. Often you have to go back to the data itself to say, okay, here is the set of data that actually led to this prediction, and then you can actually trace it back and see what's going on, because you may have some codependence of the features. That's the best I can do without actually looking at the data set. As far as like Spark is concerned, you can distribute out and do different algorithms across different workers, but that'd be a little bit unusual. So you typically would do like a single algorithm and distribute all of that across the same, a set of hyperparameters, and then be able to then do feature selection based on whatever features have the more importance. Does that answer your question?
Thank you.
Oh, yeah, sorry. Yeah.
Just real quick, in terms of the termination of the process, what do you do to persist the exhaust from this, the result? Are you updating edges in Neo4j or Jupyter? Or what happens?
There's a talk actually tomorrow, and I don't want to steal his thunder, about how to like persist and have this idea of what's it called, model governance, or as well as doing model provenance. But I'll save that for next time. You can checkpoint manually. You can also save off the model at different points. You can pickle it. Those are the options, but we'll talk more about that tomorrow.
Hello.
I think we're good.
So,
Unless you want a little more.
yeah,
Oh.
I have a question. So, for the technical one you talked about, how would you deal with a sparse matrix? For example, if you get your data from one-hot encoding of categorical variables, how would you convert that back to a pandas state frame?
Oh, that's a great question. So if you vectorize it as a sparse matrix and then do two pandas, it'll maintain it as a sparse matrix. It'll be a Apache Spark sparse matrix object. It'll have basically the number of the width, and it'll have each of the different values when it's not zero. It'll have all the values in it. As far as how do you do that in scikit-learn, I have to look it up. I don't know how to translate a sparse matrix in Spark back to like a sparse matrix in pandas, but it should be possible. So I wouldn't convert to a dense matrix. That would cause other problems in your system. We have one more question, Jules. Okay.
You got it.
This young lady.
So you mentioned that for parallel training, you kind of load the data in memory. My question is it data parallelization or it's model parallelization? So when you distribute or is the data in one place in Spark and then you have sort of the shared data between various nodes, or the training is in parallel where you're kind of remembering what are the gradients?
Yes.
So that's my first question.
Yeah. So you have cache, and then you also have data coming in from distributed file storage, whether it's HDFS, blob store, S3. And at no point do you actually take all this data and actually collect it back to the driver. You're only calculating some calculation, whether it's a gradient or some other calculation, depending on the type of model.
Right.
So the data is staying in the workers, so you're not going to actually have a situation where you bring so much data to the driver that it crashes. Now, the driver is a single orchestration engine in Spark, so you have to have a driver in order for the program to function. But if any individual worker crashes, which could happen on long training runs, then it'll recompute based on a new worker what the value should be.
So you have the copy of the data in every worker node, right?
We have data, you don't have a copy, you have a partition of the data set in each of the workers.
Got it,
Yeah.
okay. So the second question was, what are the techniques that you use to sort of aggregate your gradients or what model learns and sort of get back to the driver, and like what do you choose? Like how is that decided?
Yeah, a lot of it's done using Breeze, and I have to look at this. I haven't looked at this in a while, but using Breeze, so you're actually doing a tree aggregate. It's actually doing the matrix computation and then aggregating that overall computation.
We have a question here.
One more?
Hi. Sorry, so I just wanted to know how important. Hello.
Oh, there you are.
I see.
Sorry, it's a big room.
There's obviously we've got lots of different types of machine learning algorithms, but I know a lot of them are based on linear regression, and some of their steps use linear regression. So how important is it in general to check for the conditions of linear regression in your data set before you actually put it into a model?
That's a great question. I mean, I usually check a handful of variables to see if there's linear correlations, or just run a linear regression and see how big my coefficients are. If most of my coefficients are 0, then I probably have no nonlinearities in my data set. And I'll try a nonlinear method. So one thing to note is that most data scientists will start with linear regression or logistic regression because they deal with generally small data sets. But as you add more and more data, you may want to try a more complicated method, whether it's a neural network, random forest, gradient boosted decision tree, because when you add more data, you're not able to actually represent those nuances of that data set in linear regression because you're only fitting a line. So your line can only get so straight. So oftentimes you'll want to experiment with a few different methods.
Any other questions on this side? Okay, here you go.
Yeah, so let's say you have a data set that's like 90% in one class, 10% in another class, and I wanted to have each batch take, let's say 8% of that one, we're saying positive class, and mix it in with every single other batch of randomly selected 8% from the 90%. Could you do this using this?
Yeah, you could do that with the Spark. I didn't do it here in the demonstration, but what you would do is you do a simple group by or where clause. Let me see where I found my splits. Oops, did it over here. Apologies for the scrolling. So here where you do random split, you would just split based on a subset of the positive class and a subset of the negative class, and you adjust your percentages either way. So you typically want to upsample your or downsample your negative class and upsample your positive class, and then get to the right balance so you don't have imbalance in your model.
We got 4 minutes. We're going to take a couple of more questions.
Okay.
All right, Thunder, go ahead.
Yeah. So in the case of the random forest, for example, in which you need to transform all features or categorical features into numerical features, what's a good strategy for dealing with missing values at prediction time?
That's a good question. I mean, there's no science to missing values. I mean, I'm going to tell you the same thing everyone says, which is doing mean impute or doing zeros. There are some decision tree algorithms that do splitting based on a missing value or unknown value, but that's not necessarily better or worse than the mean. So it's not there's no I would say established science on that. I'm sorry, I didn't answer your question, but that's as much as I know. Yeah.
I just want to look at the slide before with the cluster manager and the distributed system. So I'm just curious if everything works like synchronously, asynchronously. Can you give me a little details about the cluster management?
Can you repeat that?
Can you give me a little more details about the cluster management when doing the distributed learning?
Yeah, I can talk a little about cluster management for Spark.
Yes. So is it like asynchronously designed, or does the user can like define, configure like synchronous or asynchronous? I think most of the time, like synchronous systems are what we think, but I'm seeing like there's a lot of people trying to do asynchronous learning as well.
Yeah, no, it's a great question. So Spark isn't an HPC architecture. It's closer to MapReduce. So it's so much of a shared nothing architecture, like with the exception of the driver. So what happens is the driver will submit a command out to the cluster, and then it'll distribute out that computation across all the different workers. If for whatever reason a worker dies, it'll get restored, and then it'll recalculate whatever was going to be calculated based on the DAG for this individual worker. So it's not HPC. And the cluster manager for Spark varies depending on your actual architecture. So in Databricks, we have our own cluster manager that our team has written. There's also obviously Mesos, Kubernetes, Yarn. So it really depends on those individual scheduling systems, like how the actual cluster manager behaves. Depends on those really.
Kind of aside from compute power, one of the main reasons to go with a distributed system is to kind of scale out your memory. I was wondering if you have any heuristics or thoughts about how to like estimate how big of a cluster, how much memory you might need for a given algorithm.
Oh, that's a great question. So it depends on the framework you're using as well as the amount of data. So the way I typically do it is I look at like a single row of data and I will subsample it and then look at the memory usage, because you're going to have some overhead either based on pandas or the JVM, et cetera. So once you add in that overhead, you can figure out the overhead. Then you can do the multiplication on how much memory you need. That's how I typically do it. But it's one of those things that's pretty hard to predict. It really depends on both the framework you're using, the algorithm, and the nature of your data set.
All right, give a big hand to Richard. Thank you, Richard. And we're going to have a second speaker, so a couple of minutes before we actually hook up. Alex, go ahead and just put your stuff in. Richard, can we have your mic? Now, while we're actually dealing with the miking people up, I just want to ask a couple of questions. How many of you have crossed an ocean and across a continent? Now, Databricks customers or Databricks employees don't work, so we're gonna. Where are you from? You're from Australia. What town? What city? Canberra. Okay, remember that, Canberra, and we have to find out the distance between Canberra and San Francisco. Who's the next? Anybody can actually beat Canberra? Yeah, where are you from? Japan. Well, what city? Tokyo. Okay. Is Tokyo farther than Canberra, Australia? I don't think so. All right, where are we from? Korea. Seoul? Okay, and you? From where? Ukraine. Where? Kyiv or Odessa? Kyiv, all right. Anybody else? Okay, so I think we have a contender. We have in Australia, and we have, yes. Joburg. That's, you should have said Cape Town, then I would have actually favored you because, it's hometown. So I should just say Cape Town, all right? So we've got Australia and we've got Cape Town. Sorry, guys. So you got T-shirts for both of you. Come and get me when we are done. Thanks for coming, crossing the oceans and crossing the continent. Okay. Now today, if you attend any of the big data conferences like this one today, invariably you'll actually find a lot of talks on machine learning and distributed learning on TensorFlow. In fact, we actually have a couple of tracks tomorrow which are dealing with deep learning techniques, and TensorFlow seems to be one of the default platform. And we have made tremendous strides in distributed computing, not only because of the fact that the machine learning algorithms and the frameworks have gotten smarter, but we can actually deal with building large-scale data pipelines. And Alex is one of the engineers who actually created Horwood at Uber, which actually allows you to do distributed learning in TensorFlow. So he's here to talk about how to actually use that platform. So give him a big hand to Alex from Uber.
Thanks, Jules. Can you guys hear me? Yeah, seems like you can. Okay, awesome. So I'm Alex. Nice to meet you. I'm working in the machine learning platform team at Uber, and I work on deep learning and distributed deep learning. So today I'm happy to talk to you about Horwood, which is our library for distributing deep learning frameworks. And so first slide is kind of motivational slide that it's at this point famous slide by Andrew NG. And basically what it says is that as you grow amount of data, you have to switch from using these traditional machine learning algorithms, which are very fast, work very well, to deep learning algorithms in order for you to keep increasing your accuracy, which in this case is marked as performance. And so that's why companies who are traditionally used normal, like say linear regression and decision trees, are now looking more and more into deep learning because the amount of data that they're collecting is increasing and they have opportunity to get better accuracy if they do so. And so at Uber we have many use cases for deep learning. Some of the more obvious ones are self-driving vehicles, which involves cars and trucks. Trip forecasting, where we want to know how many people will request cars today, in 5 minutes, or in the new year. Fraud detection, to make sure that there is no fraud intents happening on our platform, and many, many more. And so in most of those cases, traditionally we're using a non-deep learning approach, and as we grow amount of data, we've found that using deep learning helps tremendously. So how does it work, and why it's called deep learning? So in deep learning case, what you have is a model, and so you feed data on one side, get prediction on the other side. And as data goes through a model, it goes through a series of nonlinear transformations. And as you can see, sometimes it's basically directed graph. So you can see that in some cases you might have forks and then joins. And so when you do training of such model, you basically supply both data and known prediction. And the training goes as follows. First, it does forward pass to get prediction. And then prediction gets compared with the actual true label. And so if there is any difference, then gradients will get computed all the way from the bottom of the model to the top. And After that, the model will be updated. So there is, first part is called forward pass, and second part is called backward pass. So at Uber, we use Tensorflow a lot, and there is many good reasons for that. One is that it's most popular open source framework. So what it means in practice, it means that it's first very reliable, and second, there is a lot of examples. So when we have new data scientists starting who may not know deep learning, they have vast amount of resources online to learn about it, and also any new research and any new model architectures very likely have implementation in TensorFlow. TensorFlow also allows you to both have good performance if you use high-level primitives. So for example, if you use Keras, which can be can run on top of TensorFlow, you can define your model in, let's say, 150 lines of code. At the same time, if you want to modify that model and optimize one of the pieces of the model to run super efficiently on GPUs, and you write your own so-called CUDA code to do that, you can do that with TensorFlow. So you can take 150 high-level lines and add your custom primitive, which can be built by sophisticated engineer who knows CUDA, and then all the data scientists in your company can use it. And also it has end-to-end support from research to production. So it's pretty easy to set up research models. You can play with the framework. But then if you want to do production inference using Python or C++, TensorFlow has a very good way to go from A to B. And so as you get more data, you can start thinking about doing distributed training. And typically there is two ways to think about distributed training. There is model parallelism and data parallelism. So in case of model parallelism, you have one big model that doesn't fit on your single computational device. And so you get stream of data, and you actually have to compute your model by splitting the parts of computation on different devices. Whereas in data parallel case, you actually have copy of the model on each of computational devices, and then you read different parts of data. So in this talk, we will mostly talk about data parallel use case, and here's a few reasons. One is, since this is deep learning, most of deep learning you run on GPUs, and modern GPUs have a lot of RAM. New voltage GPUs have 32 gigabytes of RAM each, which is quite a bit. There is new techniques such as gradient checkpointing, which actually allow you to, if 32 is not enough for you, you can use gradient checkpointing and trade off computation, let's say 10% more computation, for 2 times bigger model. So there is good amount of leeway that you can have to fit pretty big models on existing GPUs. And at Uber, we found that vast majority of our use cases were actually data parallel, so that's where we focused our efforts. That said, you can still use this technique to scale up to few computational devices within a server. So assuming your model fits into, let's say, 200 gigabytes, you should be able to leverage this with modern GPUs. And a lot of this were inspired by Facebook when they published the paper where they trained ResNet on ImageNet in 1 hour using 256 GPUs, which was very great achievement because before that people were training ImageNet for weeks, and that was quite a big achievement. And so here is the picture of how data parallel training happens. So you have, as I mentioned, you have training processes, each of which has a copy of the model. They all ingest different slices of data, compute gradients, and then they need to average gradients. And that's where the secret sauce happens. And then those average gradients get independently applied. So traditionally, when you use TensorFlow, the technique that is widely described is parameter server. And so that's what we tried first. We tried to learn, and basically there is all these concepts about parameter server that we had to learn. And what we found is that most of the data scientists were not able or not willing to learn those concepts. Basically, it was too much effort for them. And second problem was that parameter server typically encourages one of two architectures. Either you have all parameters being on a single server and all workers would communicate with it, and so then you have bottleneck, or you have many parameter servers and many workers. But if you scale this paradigm to, let's say, tens or hundreds of servers, your network infrastructure will quickly get unhappy. And this is example script with parameter server technique. So one of the problems with with that our data scientists felt is that basically instead of focusing on the model, you have to focus on many, many things, each of which is very easy to get wrong. So we thought, okay, what can we do better to serve our internal customers? One is we could think maybe for data parallel use case where you basically replicate exactly the same model. You don't need all this vocabulary of parameter server modeling. Also, we could use different communication algorithms. So instead of one tool or all tool, we could use something more clever. And lastly, we had hardware, which was, our servers had RDMA capable network because it was built by people aware of HPC. And so we wanted to leverage that because it allows lower latency communication than using traditional TCP/IP. And so we built Horvath. So Horvath is distributed training framework for Tensorflow, and it's inspired by work of other companies before, so Baidu, Facebook, they all did a very good job. It uses bandwidth optimal communication protocol, so it uses so-called technique called ring all reduce, which I will cover next slide. It can install next to TensorFlow, so you don't need to have custom version of TensorFlow. You install TensorFlow, after that you install Horvath. And it's also named after traditional Russian folk dance where everybody dances in a circle. And here's why. So the Horvath technique is called ring-all reduce, and Patarasyuk and Yuan claim in their paper that it's bandwidth optimal technique, which means that if your buffers are large enough, then this is the best way to use your bandwidth in your network. So how it works? Let's say, so this is an example, you have 3 workers, each worker has a buffer with 6 numbers. And the goal is to get sum of every number across all the workers. So what happens is every buffer will get segmented, in this example, to the number of workers. And so there is 2 phases of algorithm. In the first phase, workers exchange data. So every worker will send 1 piece of the buffer to another worker and receive 1 piece. And it will do summation, so which is on the top. And then after that, every worker will have 1 piece which corresponds to ground truth, result of summation. And so next phase is just to distribute that information across all workers. So while it takes multiple steps, the good part about it is if your buffer is large enough, you can actually amortize the cost of this to be very efficient, almost to the point where you send the buffer once, the whole buffer. And so how does Horvath stack works? So we use custom operation to plug into TensorFlow, and we use MPI for worker discovery and coordination. So the reason we need coordination is in that slide before, there were splits. And so what happens is TensorFlow can actually compute those splits in arbitrary order, and on different machines, the order can be different. And so that's why we need to coordinate between workers to know which pieces of information are ready to be reduced and which are not ready yet. And so that's why we use, partially why we use MPI. And lastly, for actual all reduce, we use Nickel, which is NVIDIA's super efficient implementation on their GPUs. So here's code example with Horvath. It contains basically 4 modifications that you need to make. So one is you initialize the library. Second, you need to tell TensorFlow which GPU it's supposed to use. So in this example, what we do, and this is super common, if you have server with, let's say, 8 GPUs, what happens is we would run 8 different processes on that server, and every process will use just 1 GPU. What it allows you to do is, you as a data scientist, you only think about your deep learning as a problem of using single GPU and training a model on single GPU. Then after you make those code modifications, you can train it on 1,000 GPUs with exactly the same code. And so after you told TensorFlow which GPU to use, you wrap optimizer and distribute optimizer, and that's what injects the secret sauce all reduce into the computation. And then you add this hook, which will make sure that when you start the training, if you start from scratch, every worker will have different version of model created from random weights. And so you don't actually want that. You want to start from a single spot, and I'll show you why later. So the good part is, this is an example for TensorFlow. For Keras, it's actually very similar. So it's exactly the same for pieces. It also works with new estimator API. And now it also works with PyTorch. So before it was just TensorFlow, now it's also PyTorch. And the way we refactored the code allows us to add more frameworks in a pretty easy way. So if you guys have favorite framework, you can send us pull request. So with PyTorch, it's also exactly the same set of steps, which is very convenient, especially for us, because while a lot of our training is in TensorFlow, some of our researchers like to use PyTorch. And so sometimes they train a model on TensorFlow, sometimes on PyTorch. It's very easy for them to transition between distributing one and distributing another because steps are the same. And so how do you run, let's say you have a bunch of servers, how do you run Horvath? Simple way is you install MPI and you run these commands. Usually what happens is in your organization you will have some infrastructure team which owns servers. And so that infrastructure team, at Uber, that's us, make some convenience script. So you hide all these flags in the convenience script, and then you just say npm run.sh, python train.py. Then for data scientist, life is very good. On Spark, Databricks published very good article, how to run Horvath on Spark. And so I encourage you to try it out. And look for, they were also working on even better way. So look forward to announcements this week. And so let's talk also about performance. So Horvath, one of the key factors for us was actually simplicity. Very first goal was to make it super simple and make it work. And performance was actually secondary goal. But what we found is that this model actually scales very well. So it scales to, we did internal testing with 500 GPUs, but there is some research organizations that pushed it to tens of thousands of GPUs, and it still works. So in this case, up to 500 GPUs, we saw 90% scale efficiency when we use RDMA. And then if we don't use RDMA, depending on the model, you will have some performance downgrade, but not significant. So if you're using normal ResNets or image or Inception, you will get maybe a few percent inefficiency. If you do VGG, it's going to be more, just because VGG has fully connected layers, and it's also a very short model. So your time to do this whole reduce is very short, but the amount of information you need to share is very large. So depending on your model. If you train big models, then usually your scaling is very good. And so now I'm going to cover a few practical aspects. So one aspect I mentioned is initialization. So I actually want to make sure that you initialize from the same spot. If you don't initialize from the same spot, you will have a situation like this. So you have two workers, they both randomly initialize, they both compute gradients, then we average those gradients, and they don't point towards minimum. So in order to avoid that, you need to initialize from the same spot. The second aspect is data partitioning. So data partitioning is interesting because different frameworks encourage kind of different techniques. And so, tip one approach is to do deterministic. So basically, every time you shuffle data set, you split it into chunks for every worker, and then every worker will read his chunk. Then after that, data set will get repartitioned. So PyTorch uses this model a lot. And dataset API from TensorFlow also uses that same model. Another approach is to just do random reading. So let's say you have 10 workers. Each of them are given the full view of the data set, and they just randomly read data from the full data set. And that's more typical with things like Keras or normal TensorFlow before dataset API. And so what we found, we did some experiments to see whether we should prefer one or another, strongly or not strongly. And so what we found is that while this approach potentially can cause some records to be just read once, and then some records to be read multiple times, or some records never, we found that for most models, like for example, ResNet, training on ImageNet, there is no difference. So if your training is training across large enough number of epochs, and your examples have similar significance, you would not notice that much big difference. And so conclusion is you can use whatever method is most convenient for you. And one caveat here to remember is while you're distributing your training, so let's say you just split 90 to 10, and you distribute your training, so your training now takes 10 minutes. But you didn't distribute the validation. What will happen is your validation will actually start taking longer time than your training. And so what you need to do is for validation, you also need to validate on subsets of data. And Horvath comes with a callback that allows you to average results of that validation if using Keras. If you don't use Keras, it's super simple to write it yourself. If you use PyTorch, our GitHub also has examples how to do that. Other aspect is, so let's say you use Horvath, you modified your model, and you process so much more examples per second. If that's all you do, it will not converge faster, which is ultimately what you want. You want to get your model super quickly. And so there is multiple techniques. First technique by Facebook allows you to train to certain batch size. For vision models, it's up to batch size 4,000 to 8,000. And this technique is very simple. You just multiply your single GPU batch size to the number of GPUs that you're going to train on. And one of the features is also you need to do this warm-up that you can see on the top left, basically from the beginning to a certain amount of epochs, you linearly raise your learning rate. Or you can do some variations. For example, you can do gradient clipping. And so this allows you to scale. This is how they did this 256 GPU image training in 1 hour. And Keras version comes with a callback that you can just drop in and it would do all these things for you. There is more advanced techniques. So one is called LARS, Large Batch Training for Convolutional Networks. And there they were able to get to the same accuracy with 16K total batch size. And with 32, you get a little bit worse accuracy. And so in this technique, they actually used per layer adaptive learning rate schedule. So if you have that many GPUs, encourage to read this article. And then if you have even more GPUs, like some of the people who do research on supercomputers, there is another interesting paper published by Google, don't decay learning rate, increase the batch size. So let's say you used first technique to scale to 4,000 batch size. And now it's time for this decrease in learning rate. In this case, it's by, I think, 5 or 10 times. So instead of decreasing learning rate by 10 times, you can actually increase batch size by 10 times. So you can go from 100 GPUs to 1,000 GPUs at this point and keep the same learning rate. And so basically, in this case, if you have these 3 steps and you have infinite amount of GPU, by some good luck, you can train your model 3 times faster. And then depending on your learning rate schedule, you can train even faster as well. And so at Uber, we use Facebook's learning rate technique a lot because seldom at this stage you get models that require thousands of GPUs. We use Horvath exclusively for distributed deep learning. And we train both convolutional networks and LSTMs in hours instead of weeks or days that it used to take before. So for most data scientists now, they actually prefer to use distributed training just because they can iterate on problem much faster. And then Horvath is adopted in many companies and many research organizations who have clusters as small as single server, but it's just convenient to use, to some supercomputing facilities where they have tens of thousands of GPUs. And so that's it. It was about a little bit quick, so there is a lot of room for questions.
Thank you, Alex. Any questions? You heard it from the horse's mouth about Horvath. Any questions? All right, here you go.
Hi, thank you for your presentation. Actually, there's one thing I really wanted to know is network topology of the networking system or your environment? Is that fat tree?
Yes, but with Horowat, it's not really a requirement. So the way we schedule these workloads using scheduler, the optimal way is to do tight packaging of servers on the cluster. So let's say you have racks of servers, and you have top of rack switches, and you have core switch. If you do tight packaging of servers, because of the way ring algorithm works, you actually need to cross the rack only for two flows, one in, one out. And even for core switch, you also have one flow in, one flow out. So if you provision enough that your training doesn't span too much, then it should be fine. That said, in many cases there is fragmentation issues. For example, people run some small jobs and then you have a bunch of free machines here, free machines there. So it's definitely a challenge. But it's among different algorithms, this is probably the one that is most friendly to networking.
Okay, thank you. Actually, there's one more question. It's about the underlying system or underlying file system or your system. Is that a local system or can be some kind of distributed file system?
So we use various things. We use, simplest way is to actually use local file systems. So you have data somewhere, you can download, let's say, train on 100 servers. Your data is too big, but you can, if you split it 100 times, it may be okay to put it on local disk, and then you will get very good performance. Other way is you can stream data directly from distributed file system like HDFS or S3. Third way, you can use things like NFS. We found different use cases prefer different things. NFS is actually most data scientist friendly because you can go inside the LS, see all your files, play with it, and there is zero barrier from reading in your code. But other file systems require you to use more sophisticated APIs.
Okay, thank you. Actually, there's one more question. Okay. So, okay.
There is a lot of time.
Last one. So you mentioned that you used MPI. So I'd like to know, do you use like MPI-IO for like file system, I/O?
No, we don't use MPI-IO. However, with Horowat, you can actually, it can coexist with MPI, and some of our applications use MPI for Pi. So with MPI for Pi, I think you can use I/O as well, but nobody in Uber does it. What we saw is common use case if your validation is very sophisticated. Like for example, if you're doing some detection model and you want to compute some very interesting metrics, it's pretty hard to do distributed validation and then collect all the data using simple, like all averaging, for example. So what they do is MPI for Pi allows you to do all together very efficiently. So not efficiently, but rather easy. So you can actually throw Python object to it and it will serialize it, transform, transmit over a network and unpack on your master. So that way it's actually super easy to do things like distributed validation.
Okay, thank you.
Do you have any questions on that side? Thunder, yeah, go ahead.
Yeah, so when does it combine the gradients? Like at what point does it do it at the end of a training or does it do it during? And also dropout. Does it drop out in just one on one server and then distribute that, or does everyone do a random dropout and then combine that at the end?
Okay, so for whether this process is, okay, so here what happens is as we do backwards pass and gradients are computed, we actually in parallel start to reduce them. So as let's say gradient 5 is being computed, gradient 6 is already being averaged across servers. So in that sense, it's making computation and communication parallel. But your second question I didn't catch. Can you repeat that?
So dropout.
Yeah.
When you apply dropout to the network, how does that, using this model, how is that distributed? Because you do...
So every worker will do dropout independently, and then gradients will get averaged.
Interesting, okay. And have you ever experimented with where you communicate that information across? Have you ever just let it run and then at the end?
No, so for both dropout and batch norm, we actually allow them to run independently on every GPU. And for dropout, I don't know about much research, but for batch norm, people actually recommendation is that you keep it to single GPU, especially if your batch size is like 30 to 16-ish. Because if you try to compute batch norm over a large batch, actually it loses efficiency. But then there is some interesting cases where, for example, detection models are big. And so if you use not very good GPUs, not the ones that I was mentioning, but less good GPUs, your batch size may be only 1 or 2. And in which case, it's hard to train batch norm. And so that's one of the areas where there is no good solution right now. There is some research into things like batch array normalization, where you, instead of doing batch norm, do some other math. But so far, they didn't get as good results. And so if that's something important to people like you, there is definitely direction where we could make it supported.
I got a question over here. I hope it's not 3 questions in a row.
Thanks for your talk. I have some questions regarding to, you talk about that you can, with the framework, you can work with distributed file system like HDFS, right? So in terms of resource manager, there is a way to connect this framework with resource manager like Yarn or Mesos?
So we actually at Uber will run this on Mesos. We use a proprietary scheduler on top of Mesos right now, which I'm hoping we will open source. It's also possible to run it on Kubernetes, and there is few examples out there how to do it, both using Kubeflow and Helm. So there is definitely many ways, and then with Databricks, they run it on something. I actually don't know what the scheduler is.
Okay, thank you.
I have a question. So when I'm doing model search, a big part of my problem is that I don't a priori know what the right architecture is for my deep learning. So I spend a lot of time trying out different architectures. What's the workflow for trying out different architectures that your data scientists usually use?
So actually this is where Horowitz is very helpful, because if your model is big, without Horowitz, your experiment takes weeks. And so you will get data point about efficiency of your set of hyperparameters after 2 weeks. With distributed training, you can get results after, let's say, a few hours each, and then you can modify your search space. So typically, when people want to do hyperparameter search, these days, best ways usually include some sort of Gaussian process optimization. There is both online services where you can either get some for free or pay, and you basically send them data and they give you new options to try. Or you can basically read the book about how Gaussian processes work, and there is few open source implementations where you can basically feed all the hyperparameters that you already tried, and then it will suggest you what's the best next one to try. And that's more sequential process.
So I guess my follow-up question to that then is, at what point would we want to instead just downsample our data and train on smaller single node processes? So what's the order of scale that we should be thinking about Horvath versus just Keras or TensorFlow?
I think in all cases you should strive to get, especially in the beginning, you want to have very small iteration time. So if you can do first few hyperparameter tests, every time should take, let's say, a few minutes or maybe an hour at most. And then it depends on your resources. If you have single server, you just use that. If you have a lot of GPUs that are unused, you can do distributed training and use larger data set. In general, the larger data set you try, the better signal you will get. So it's a trade-off. And it's also empirical based on your data set, on your model. In some cases, for small models, they don't infinitely increase their usability as you add more data. So it's actually, your model needs to be adequate for your data. So if you iterate on small subset, it's going to be super easy for it to overfit. And that's why if your data set is inherently very large, it's better for you to do distributed training and then train on that very large data set, because the choice of your model may be very different from what you will get if you train on a smaller data set.
Sorry, can you say an order of magnitude for what you mean by very large here?
So I would say for, let's say, ImageNet training, we pretty much, if we do experiments on ImageNet, all of our experiments are on 100 GPUs, because otherwise they just take too long.
Thank you.
Any other question? None on this side? Okay. So we got only a couple of minutes
thank
left,
you.
so we'll just take 2 questions.
Nowadays, I have seen loads of data scientists using neural networks for everything, like classical engineering. So I see this is very complex, what you're doing. So how your team decides the deep learning was the best technique to apply for the use case? We don't know what the use case is, so I was wondering.
That's a good question. Usually, actually, you should always try a simpler model first. So first start maybe linear regression or decision trees or some other traditional models to get baseline. And then after that, you can start using more neural networks or some other techniques and see whether that actually improves your accuracy. At that point, it's going to, again, depend on your data, on your problem space. Let's say vision models, there is almost no traditional techniques to do them. For just streams of factual data, basically tabular data, decision trees do a pretty good job. And unless they're super huge, it's kind of hard to beat. There are some interesting ideas about combining trees and deep learning models. So for example, you could use deep learning model to condense if you have millions of features for some reason. And you want to build decision tree model. It may not work on that millions of features because it will have to do a lot of downsampling of features. So what you can do is you can run deep learning model first to condense and represent your input examples into some smaller dimensional space, and then run decision trees on top of that. So there is the universe of models that you can try is very large, and right now I don't think there is clear guidance where to use which, but usually the best approach is to start simple and then go more and more and see at which point amount of effort and cost you have to pay to get a little more accuracy actually makes business sense.
We'll take one more final question because we've got one more speaker, so it's only fair.
Hi, thanks for the talk. Could you speak a little bit about where the bottleneck is in different trainings you're doing, and in terms of data set size? So are you compute bound, are you memory bound, or are you IO bound relative to the size of the data set?
Mm-hmm. I think it all depends on few factors. So if let's say your GPU is very powerful and your data set is pretty small and your model is pretty small because of your data set is very small, what will happen is GPU will always be starved for work to do. And that may be because it could be IO bound from your data source, or it could be even bound reading from your RAM. Or it could be CPU bound because you need to do some pre-processing. So it depends on the model. The better you get GPU, it's actually, you need to think very carefully about how you're gonna supply data to it. So that's in case of single server. As you go beyond one server, another thing that needs to be very thoughtful is network. So it's for, let's say, DGX box with Volta GPUs. Their reference implementation has, as far as I remember, 400 gigabit cards. I would argue this is probably a little bit overkill, but having at least one or two is definitely going to help with the scaling.
Okay, give a big hand to Alex. Thanks a lot, Alex, for the wonderful talk. We have one more talk. Peter, come on. Could we have Peter hook up? Yeah. We can hook it up in the. No break. We're just going to go straight. Thanks, Alex. Good talk. Just send me the.
Yeah. Yes. Yeah. I mean,
Hello, welcome back. Our final speaker, last but not least, is Peter Graft. Peter Graft is a PhD candidate at Computer Science Department in Stanford University, advised by none other than Matej Zaharia, who's going to give a keynote tomorrow and have lots of surprises, along with Peter Ballas. And he's going to talk about the work they're actually doing at Stanford called Apache Spark and MacroBase. It's really an extension of SQL operators for you to be able to do analytics at scale. So please give a warm welcome to Peter, who's going to talk about Apache Spark and MacroBase.
Can everybody hear me? Okay, so today I want to talk about MacroBase, which is a new system we've been developing at Stanford for making it easier for you to find interesting or unusual trends in your data set. So I'm going to explain what MacroBase does by way of example. So let's say that you're an app developer and you have a problem. Your app is crashing a lot and you don't really know why. In order to solve this problem, you have to figure out what sorts of factors are causing the crashes. It might be a particular version that's broken. It might be a particular localization. It might be an issue with a particular operating system or a particular phone. You don't know, but it would be incredibly helpful for you if you could find out. So you have a bunch of logs of runs of your app. Some of those runs crashed, some of those succeeded. Within the logs contain the information you need to figure out what's causing the crashes. But getting that information out of the logs is really, really hard. The problem is that your logs look something like this, and you don't really know what's going on here. If the problem is really obvious, if it's, say, one particular version crashing all the time, you can get the data out manually or with some of the tools that are available out in open source or proprietary out there. But if the problem is subtle or complicated, it can be incredibly hard to figure out what is actually causing the crashes or what's causing many other sorts of problems or irregularities in your data. So what you'd like is a tool that just gives you a nice, simple explanation, a summary of your data that answers your questions and tells you what your problem is. So you'd like a tool that tells you that, say, version 4.1 of your app running in French is far more likely to crash than any other version, and that's the source of your problem. So this sort of thing is what we call an explanation. And MacroBase's purpose is to provide you with these sorts of explanations, to answer your questions as easily as possible so that you can understand what's going on in your data. So MacroBase returns explanations. An explanation is a set of attributes in your data that answer whatever questions you asked it. So if the question you're asking your data is what's causing my crashes, the explanations might be, say, a combination of country and version, or a combination of device name, of device type, and phone operating system, or anything else that could plausibly be causing crashes. The way you get explanations from MacroBase, the way you ask MacroBase questions, is by giving MacroBase a pair of data sets and telling MacroBase to find differences between the data sets. The differences between the data sets are the explanations. So in the crash example I gave earlier, the two data sets you give MacroBase are logs from runs of your app that crashed and logs from runs of your app that didn't crash. And the explanation will be any attributes that appear far more often or in crashing logs or in some way appear to be causing crashes. And I'll explain how exactly MacroBase calculates that later. The core of MacroBase is a new SQL operator called Diff. Diff is what is the actual workhorse. It's what does all the work. It's what calculates the differences between data sets and gives you your explanations. Diff is implemented in Spark using Spark SQL, so it can scale to very large data sets in production use cases. All right, so I'm going to walk you through an example of how we can use Diff in practice. So let's start with our setup. It's the same setup from earlier. We have two tables, table success, a table of crashing logs, and table crash, table success, a table of successful logs, and table crash, a table of crashing logs. We want to use Diff to try to figure out which attributes from these tables are causing the crashes, or at least which attributes are correlated with the crashes. Those attributes are going to be our explanations, the final return values of Diff. So we're going to use the Diff operator to find these explanations. Some of the input to Diff is pretty clear. Diff needs to know what tables you're going to diff over. In this case, it's table crash and table success. Diff also needs to know which columns from those tables you want to diff over. So which columns of data do you think contain the attributes that are correlated with the crash? In this case, we're diffing over 3 columns, version, carrier, and country. But you might want to diff over more. You might want to diff over, say, phone name, phone type, or phone operating system. Now we've told Diff what to diff over. We have to tell what sort of differences to find between the two data sets. But we now have to tell Diff what sorts of differences to look for. We have to give Diff a list of rules. We call these rules difference metrics. Difference metrics are a quantification of the idea of difference. They tell Diff what to look for, what sorts of differences to find between your data sets. In this case, when we're trying to identify crashes, the sort of difference we're trying to find is sets of attributes whose appearance in a row means that the row is probably a crash and not a success, whose appearance in a log means that the log probably crashed. We're trying to find attributes whose appearance increases the probability of your app crashing. So the difference metric we're going to use here is called risk ratio. The risk ratio of an attribute is the probability that the app crashes if it has an attribute over the probability that the app crashes if it doesn't have that attribute. So if, say, version 4.1 of our app has a risk ratio of 3, that means that apps running version 4.1 are 3 times as likely to crash as any other apps. So if we can get Diff to give us all sets of attributes, all potential explanations with high risk ratios, then we've just identified a large set of attributes which appear far more often in crashing apps than in non-crashing apps, and which probably are in some way related to the actual cause of the crash. Now, risk ratio by itself isn't enough. In general, the problem with risk ratio is that it contains no notion of sample size. So that means that your data will be flooded with a large amount of low sample size noise. If somebody used your app, say, once in Luxembourg and it crashed, then Luxembourg's going to have a risk ratio of infinity and show up at the top of your results column, but that result is not enough to draw meaningful conclusions from. So what you need is a second difference metric, support, which does have an idea of sample size. The support of an attribute is the percentage of all crashing logs that contain that attribute. So version 4.1 has a support of 10%. 10% of all crashes were on version 4.1. If we put these two difference metrics together and complete this query, what we're doing basically is asking our data which sets of attributes, which potential explanations appear more than 5% of the time in crashes, and when they appear, triple the probability of the app crashing. Anything that satisfies those thresholds is probably a useful clue on our way to debugging the crash. So in this case, we run that query, and we get the result I talked about earlier. So we see that version 4.1 of this app in French has a support of 50% and a risk ratio of 4. That means that half of all crashes are on this version localization, and being on this version localization quadruples your chance of crashing. That's pretty bad, and if we were looking into a crash problem, we'd probably go drill into this further, and we'd probably find a bug on whatever changes that version made to that localization. All right, so that's an example of how diff works. Now let's talk about what the actual syntax of diff looks like and how you can use it in other cases. So diff takes in three inputs. The first input are the two tables you have to diff over. So these are the two tables you're comparing, and the explanations that diff will return are going to be a summary of differences between these two tables. In our crash example, they were the set of crashing logs and the set of successful logs. If you're trying to do something else with diff, say examine a drop in the usage of your app, then you might want to diff usage logs of your app from last month with usage logs of your app from this month to try to figure out an explanation of why people are using your app less. The second input to diff are the columns that you're diffing over. These are just columns in your data set that you believe contain attributes that might be useful explanations of whatever your problem you're trying to solve. So you can diff over as many columns in your data set as you'd like, but the more columns you diff over, the slower diff will run. The third input to diff is the most interesting one, the difference metric, which quantifies what sorts of differences you're looking for and what sorts of explanations you want. The difference metrics are how you change diff between queries and how you tell diff what sorts of things you're trying to find. In our crash example, we used risk ratio as a difference metric. So we were trying to find attributes whose presence increase the probability of a crash. If you're trying to, say, analyze a drop in usage, you might opt for a different risk ratio, a different difference metric. Say one that quantifies how much an attribute contributed to a decline in usage between your data sets. So we provide a bunch of predefined difference metrics, but you can also define your own if you want to. So now I'll give an example of what it actually looks like to use diff in real life on Spark. So this example uses macro-based SQL, which is the extension of SQL we developed on top of Spark SQL that includes a diff operator. So we're going to launch a macro-based SQL top level here just by executing a simple Spark submit command and launching this top level on our cluster. We're now going to ingest a data set from HDFS into the macro-based SQL top level as a Spark data frame. The data set we're ingesting is an open government data set of all payments made by drug manufacturers, by pharmaceutical companies, to doctors in the past couple of years, up to 2015. So the columns of this data set are going to be things like the state of the doctor who received the payment, the pharmaceutical company making the payment, and the drug the pharmaceutical company made the payment in response to, as well as the year in which the payment was made. So we're going to run a diff over this data set. We're going to try to see what sorts of changes occurred in these payments over time. So what sorts of changes occurred between 2015 and previous years. So this diff query, highlighted in red, has a slightly uglier syntax than the one we described earlier, but the core components are the same. We compare two tables. These tables are the set of payments made in 2015 and the set of payments made in prior years. We compare on three different columns, which are recipient state, then the name of the company, and the name of the drug. We use two difference metrics, which are support, with a threshold of 2%, and global ratio, a close cousin of risk ratio with a threshold of 1.3. Overall, this query is asking what sorts of factors appeared 30% more in payments made in 2015 than in prior years. We run the query, and we end up getting our result, which is that 2 pharmaceutical companies, Actavis Pharma and Lilly USA, made substantially more payments to doctors in 2015 than in prior years. And if we were interested in doing more analysis or actually trying to solve this problem, we could drill further into this and try to figure out exactly what was happening and what might have motivated these changes in payment patterns. All right, so enough about what Diff does. Now I want to talk about how Diff works. So at a high level, as I mentioned earlier, Diff calculates the differences between 2 tables. What sorts of differences it finds depends on what difference metrics you pass into it. But ultimately, Diff is going to return all sets of attributes, all explanations from your data that pass all of your difference metrics. So you could implement Diff in the most naive possible way by just iterating through every single set of attributes in your data, calculating all your difference metrics for all of these sets, and returning all of the difference metrics, all of the sets of attributes that pass all the difference metrics. This would work, and it would give the right answer, but it would be painfully slow because the number of attributes in your the number of sets of attributes in your data is exponentially large, and you just don't have the time for that. So we have to be a bit clever. And the way we actually implement Diff is as a generalization of an algorithm called a priori. The a priori algorithm was designed to solve the frequent item set mining problem, which is the problem of finding all sets of attributes in a data set, using the terminology I used earlier, whose support is greater than a certain threshold. So we're already kind of doing that. We already use support as a difference metric. So there's a relation. We saw a relationship between a priori and Diff. We decided to generalize a priori so it could calculate more. It could calculate more difference metrics, not just support. So here's the way our generalization of a priori works. The first step of this algorithm is to iterate through every single singleton attribute, every individual value in our data set, and to store 2 numbers. These numbers are the number of times it occurs. So this is using the example from earlier of analyzing crashes. The 2 numbers we're storing are the number of times that the attribute occurs in logs that crashed, and the number of times it occurs in logs that succeeded. The reason we store these 2 numbers is because we can use these 2 numbers, and nothing else, to calculate support and risk ratio of an attribute. So we do this for our entire data set, and eventually we get a list of every attribute in our data set and how many times it occurred both among crashes and among successful runs. Once we have that, we can calculate the support and risk ratio for every single attribute in our data set. So far, so easy. But the problem is that so after we've done that, we can prune using our support and risk ratio thresholds. And now we have a list of every single singleton attribute that passes both thresholds. And those are some of our candidate explanations. That's easy. The tricky part is moving on to higher orders, where the number of combinations gets out of control very fast. The key realization is that a set of attributes, so a pair of attributes, for example, can only pass our support threshold if both the singleton attributes in it also pass our support threshold. So instead of iterating through every single pair of attributes in our data set, we only have to iterate through every pair of attributes where both attributes in the pair pass our support threshold. Since not many attributes probably passed our support threshold, that greatly limits the space of pairs we have to sort through. So we can do it much faster than we can do naively. So we iterate through pairs the same way we iterated through singletons. We find out we count how many times they occurred among both crashing and successful runs. We use those numbers to calculate support and risk ratio. We prune, and then we return the attributes that survived our pruning rules as explanations. We then move on to triplets and do the same thing, only analyzing triplets made up of pairs which pass the support threshold, and then move on to higher orders until eventually we've run out of combinations to explore. And once you've done all of that, you will eventually get the same answers you got before. You'll get the set of all explanations that pass all the difference metric thresholds. So that's how Diff works in a single node. Now let's talk about how we can distribute Diff. The key realization to distributed Diff is that the a priori algorithm we use to calculate diffs is embarrassingly parallel. It can be viewed as a MapReduce, and Spark is excellent at distributing MapReduces. So after you partition your data set across your cluster, the first thing you do is the first map phase. The first map phase of distributed diff is the same as the first phase of regular single node diff. You iterate through every single individual attribute in your data set, and you count up how many times it occurs among both crashing and successful logs. Once you've done that, you do this on every single node in your cluster, every single partition. Once you've done that, you can pretty easily combine all these maps, just through addition, into one big map on your master node, which contains every single attribute that occurs anywhere on any node, as well as the number of times these attributes occurred among both crashing and successful logs on all nodes. This is the first reduce step. Once you've done that, because your entire big list is on one node, you can calculate support and risk ratio and prune as normal, just like in single node Spark and single node Macrobase. And you end up with one big list of all attributes that pass all singleton attributes that pass your support and risk ratio thresholds on all nodes. You then send this back to the workers so they know which pairs to look at. Then you do the same thing for pairs, so where the first map phase calculates the frequencies of all pairs and the first reduce phase combines them. Then you do this for triples and so on, completely analogously to our single node example. Okay, so that's enough about how Macrobase works and what it does. Now I just want to encourage you to use it. Macrobase is fully open sourced and available on GitHub. So you can check out and download the code. We have tutorials and guides up on our website to show you how to use it, both in the single node and Spark case. And it's really easy to set up and use. So if you have a CSV containing data that you want to try to analyze, you can look at it as a single node, or you can put it up on HDFS and look at it using Macrobase Spark. And I hope you enjoy this talk, and I hope you go out and do that and actually use it. Thank you.
But the question I had, other question is, it seems like this is a deterministic algorithm. Have you thought about speeding it up by testing it first on a sample, then kind of ramping up the sample size?
Yeah, we've definitely. Yeah. So Sure. Yeah, so the current version of Macrobase doesn't use sample, but we're actually actively exploring samples right now. So one of my collaborators is currently working on a version of Macrobase that uses sampling.
Any question?
Check. Yeah. What are the values you have assigned? Why can't we convert that in a regular base? Why do I need to go for microbase, like 4.0 or 4.1? I can assign with the zeros or ones or some numerical value with success and failure, which is true and false, which I can also give like a numerical value, right? So what is special like this algorithm was doing?
Can you please repeat that? Sorry.
I mean, like false and true, you can also consider with a binary values. Then you can regularly apply your algorithmic models, right?
I'm sorry. Can you please repeat that?
Yeah. So you're calculating those models, right?
Yeah.
And like you have, with your example, you have different mobile versions, which is a numerical value, which I can assign a binary digits, right? And even true or false, I can assign a binary digit. So why I need to separately calculate this, and why are you passing this to your master node? Finally, you are calculating this entire stuff and passing to the master node, and again, you are applying it to your job threads, right?
I mean, we calculated the master node so that we know which attributes, I probably misunderstood your question. We calculated the master node so that we know which attributes pass the support threshold so we can reduce the size of the attributes that we look at in the next step of the algorithm.
Okay. We have a question over here.
Yes, hi. Over here. Yeah, left and your right, right side. There you go. Thank you. Just a quick one. I like the a priori algorithm, the statistical comparison. How does it? Are there any published papers in regards to comparison to autoencoders and other more sophisticated methods for the deep learning methods for anomaly detection?
So a direct comparison here is difficult because I'm not sure exactly what sorts of metrics you want to. I'm not sure what sorts of metrics you want to compare on. Like a priori, yeah, pretty much. Like this diff is going to return exactly what you tell it to return ultimately. If you give it a set of thresholds, it's going to return everything that passes those thresholds. And whereas other algorithms aren't exactly defined in the same way, especially if they use deep learning. So it's a really hard comparison to make. We found that, basically both sorts of tools are useful, depending on exactly what you're doing. Sorry, that's kind of a cop-out.
I got one question here, Peter.
So I was looking at your algorithm. It looks like, I guess I have two questions. So the first part is that it seems like a lot of the work can be done just using simple data frame group by, and then you do calculate metric, and then you filter it, right? So why introduce a new diff, parameter? And secondly, does it work with data frame API, or does it just work with the SQL API?
Okay, so why introduce diff? Yes, we've shown that it is possible to express all diff functionality in pure SQL. It's not fast. Diff is really optimized and is capable of doing this query far faster than you could in standard SQL. So yeah, doing this by group by is actually a couple orders of magnitude slower than doing it by diff. Sorry, what was your second question? Yes. It takes in data frames. Right now, it does take in data frames. Right now, we don't expose that factor, but we are working on that, and it will work the data frame API directly soon.
Yeah, thank you for the talk. I also first had a question about how can you do the same differently, and probably you can also use regression analysis, probably, right, to understand what's causing the problem, say logs. That's my first question. If you could comment on that, and the real question is, it's called diff, but can you do to find things which are the same, maybe, kind of reverse it somehow with a function? And so how long in terms of interactions do you go? You mentioned that, interactions between the features. Is that 1, 2, or just one column that you check? Thank you.
Okay, so to answer your questions, yes, other tools can provide similar functionality to diff, such as linear regression. The Graft example I gave was deliberately a very easy one. A lot of tools could do that well, but we found that in practice, and we have deployed this at major web companies, that diff does quite a bit better than simpler tools. Wait, what was your second question? Sorry.
Yeah, can we use it to find the same rather than?
Yes, if you provide it with the right difference metric, a difference metric that analyzes similarity instead of difference, it will find similarities. But do you mean sizes of combinations?
Yeah. So is that only in your example that would be one column that you use, or it can find the difference based on interactions between 2 columns or 3, or something like that?
Right now, explanations have to contain unique values from. You can. What do you mean by indirections? Oh, sorry. Sorry, I thought you said okay. Right now we support up to 3 columns, but we could easily support more if there was need for that, if there was need for that required. You can pass in as many columns as you want, but Diff will return you explanations will contain at most 3 values from 3 distinct columns. But we could expand that number if there was need for it. The a priori algorithm works for an arbitrary number of columns.
Okay, really nice talk, thank you. Two questions really. One is can you describe some kind of use cases beyond the logs? Like obviously this is an interesting project and there must be interesting use cases behind them. And the second question is, how does these scenarios are different from, for example, a binary classification, right? We have 2 data sets, but these data sets can be seen as one data set with just 2 classes. And we want to kind of, have some reasonable score of combinations of attributes for those classes, or even an information retrieval problem in which you want to rank sort of the. How does this diff compare to those other scenarios? And trying to understand a little bit more about the use case, what kind of real scenarios we're talking about.
So the crash example is a canonical one, but another scenario in which we found diff could be pretty useful is time series analysis, where the 2 sets you're diffing are going to be sets from 2 distinct periods in time. And then diff will try to find differences in something you specify between those time periods. So a concrete example might be, I kind of alluded to this in my talk. Let's say that you're trying to analyze changes in usage rates in usage of your app over time. You could define a difference metric that returns all attribute, that associates a usage metric with each attribute. So calculates the average of the usage associated with an attribute in the same row as the attribute, and then finds all attributes where the amount of usage associated with them has dropped over time. So you might find that like a particular demographic category is using your app much less in one time period than another. And that sort of thing can't really be, it's doable by other means, but can't really be done in this, it's nowhere near as easy to do with other tools as the crash example is, because the notion of averaging is like a harder thing to aggregate and think about.
In this, how do you manage complex data types, like if it's an array or list within the column? How does that behave, and is there any plan to do diff between unstructured data, say XML, JSON, or things like that?
So currently diff is implemented as a SQL operator, so it takes in only relational tables.
Okay, thanks.
Thanks a lot for your talk. I wanted to kind of piggyback off one of the other questions that was asked earlier, which is that diff can be implemented as a series of like handwritten like group bys and existing like SQL operations. And we mentioned that diff can be optimized to be faster than just running those operations by hand. I was wondering if you could explain how that's actually done, and maybe in a little bit more technical detail there. Some of the things that we know about SQL is that you can write custom optimizer rules. You can plug it to the Catalyst framework. I was wondering if you guys were doing something in that space to do that.
Yeah, you could implement diff as a series of logical optimizations in the Catalyst optimizer if you wanted to, and we've actually thought about doing that. It would work, but although the actual syntax required to express diff as group bys is so painful that you probably wouldn't want to do it that way, but you could do it. I mean, the actual implementation of diff looks nothing like the way SQL would do this, basically, because what SQL do is hopelessly naive. You could write something more sophisticated into a logical query optimizer if you wanted to, but at that point, you're just re-implementing diff inside of Catalyst.
Okay, we only got a couple of minutes, so if you have one short, quick question, we'll take it and then we'll wrap it up. It's been a long day. Any more questions? Going once? Going twice? I'm doing my Fitbit steps. All right, well, thank you all. Give a big hand to Peter Graft.